Hello students, this is the Chapter 14 review for the portion that looked at Hooke's law. So that was springs, and can actually be used for most things that are kind of stretchy and elastic, like rubber bands and stuff like that, or at least it can be used as an approximation for those things. So let's recall the important information first about the equations. This is actually Hooke's law and what people are referring to. It talks about the force that, I'm going to use a spring here for my examples, the force that a spring might push back with given a couple parameters. First, we have the displacement from equilibrium. That's our x value. We don't use the normal d for that, for displacement, because it's not truly just a from point A to point B of the spring. What you have to do is you have to take a spring, so I'll draw one over here. Let's say that if I'm not doing anything, this is the particular length of my spring out against the wall here to the left. Then what I'm going to do is I'm going to stretch this spring out to this particular location here. The x value is how much it actually was stretched, and so it is the displacement from equilibrium. And what we're saying is that this portion right here is the equilibrium. So if you're just leaving the spring alone, that's how long it'll be. So that's our x value, and we're going to keep that in meters to do these problems. Then up here, this k is the spring constant. That is a property of the spring. That's the thing that describes how stiff the spring is. And you may recall me holding up a spring from a trampoline where it's very rigid, very stiff. That would have a large spring constant compared to another little small spring that's very easy to move around. In fact, if I remember that the units of the spring constant are newtons per meter, I can look at this and I can make a judgment about the spring constant by saying that if I took this spring and I made this 1 meter here, so a lot of springs can't stretch out that far, but if we did that thought experiment, we said that I'm going to stretch it 1 meter, and maybe it took me 8,000 newtons to stretch that out 1 meter. So I had to use 8,000 newtons of force to stretch the thing out 1 meter. Well, you are looking at the spring constant right there with units of newtons per meter. So my spring constant would be 8,000 newtons per meter. That is a property of that spring, so that would be something that I could always carry, for example, from a part A to a part B in a problem, as long as it's the same spring. This other equation that we have here still looks at these same parameters, the spring constant and the displacement from equilibrium, but what it tells us is the amount of energy that is stored within the spring, so the elastic potential energy. I'll briefly remind you that if I had a graph that was looking at x and F here, so the force associated with the spring as you begin to stretch it from equilibrium, it should be a nice straight line if it's actually going to follow Hooke's law, and so we're going to assume all of our springs follow Hooke's law. I would have my meters here and I would have newtons here. I guess I should label that up. Given that the equation for a line generally is y equals mx plus b, I am showing that this is going through the 0 down here in that intercept, so b goes away. You'll notice that this equation looks an awful lot like Hooke's law. In fact, I have the force is equal to the spring constant times x, where by coincidence this x is the same variable there. But you can see that the slope, which is m generally, is actually the spring constant. And so I'll remind you that the slope of this line is equal to the spring constant. And we went through a small derivation that could lead us to the understanding where the area underneath the curve here happens to be a triangle. The area underneath this curve, 1/2 base times height, could lead us to this expression. So if I take the area of that triangle, I'm actually going to find that I have come up with an expression for the amount of energy that's stored in the spring. As long as this is in newtons and that's in meters, the energy will be in joules. The last thing to talk about with this is this minus sign throws people for a loop sometimes, and it really is pretty straightforward. It is a direction changer. If I'm going to talk about my force up here as a vector and this displacement from equilibrium as a vector, those vectors need to have directions. This negative sign that's in here is a direction changer. If I push on a spring, well, the spring pushes back in the opposite direction. That's all that minus sign is used for. You also know that on our equation sheets, often we just have the equation look like this, kx. All we are saying there is you need to keep track of the directions yourself, and really I guess we're just looking at the magnitudes of things here, and we're saying that the magnitude of force is going to be equal to the spring constant, which is a scalar, times the magnitude of the displacement from equilibrium. So let's take a look at a problem. Let's say that I have a platform with a spring on it, and normally this is going to be, let's say, 8 cm. Then what I'm going to do in some later moment is I'm going to place a small mass on top of that. Okay, so here's my mass sitting on top of the thing. The spring gets compressed some, and it's going to go down to 5 cm, 5 centimeters. Okay? And I'm going to say that this mass is, let's go with something like 600 grams. I would like to know what is the spring constant, and I would like to know what the potential energy is. So K, that's a script K equals question mark, and also what is the potential energy that's stored inside of this spring. First, what we want to do is we want to make sure we know what the spring constant is before we can even address what the potential energy is all about. Let's look at the information that's given. If this is my equilibrium position here, 8 centimeters, then I come down here and I say, well, what was my displacement from equilibrium? So I'm looking at the x value here. The x value is the difference between these things, and so it's only 3 centimeters. That's how far it was displaced from equilibrium. I'm not going to, by the way, I'm not really going to worry about using the signs. I'm going to keep track of it. Again, the sign, what it tells me is that this moved down, but the force is going to be up. So the x was down, but the force was up. That's what I mean by the direction changer. So the spring is actually applying a force up to keep that mass from accelerating. Okay, let's go back to x was 3 centimeters. I'm not going to like being in centimeters, and so I'm going to do a unit conversion on that, and I'm going to say that x is 0.03 meters. I also would like to do a unit conversion on this mass. 600 grams, that's going to be equal to 0.6 kilograms. And I can recognize that the Fg pushing down from this mass is actually equal to the force that's pushing up from the spring. So those forces are one and the same in magnitude. I'm going to now alter this 0.6 kilograms into newtons by multiplying it by 9.8. So I have 0.6 kilograms multiplied by 9.8 meters per second squared. That's, I'm doing the weight, Fg is equal to mg, by the way. So the Fg, the weight of that thing, Fg is 5.88 newtons. And I already had that my x was 0.03 meters. So now I'm going to use Hooke's law, and I'm going to say that 5.88 newtons is equal to the spring constant, script K, multiplied by 0.03 meters, and I find that K is equal to 196 newtons per meter. So that is the property of the spring. That allows me to answer that first question, and now I'm able to address the potential energy. Recall what I said earlier in this video. Typically you might pull the spring constant from part A to part B. because it is a property of the spring. So as long as you are using the same spring, it's valid to do that. So now I just have to say the potential energy held within that spring is equal to 1/2 the spring constant times x squared. It's going to be nice and easy. It's the same x that I had before. I now have my spring constant. This is newtons per meter. And I have 0.03 meters, but that's getting squared. When I do this calculation, I find that the potential energy is equal to 0.0882. And this is actually in joules now. I could see that because I have over here on this square, that's going to move into the parentheses here. So I actually have meters squared over here for units. One of those meters will cancel one of the meters over there. And my units go to newtons times meter, which is the same thing as a joule. So the potential energy held is 0.0882 joules, and the spring constant was 196 newtons per meter. So I think that's all I have for you for this, guys. If you think you got it all figured out, let your computer know.